You're asking the DCD. Right. So, are you getting a back then?
Not taxing. This is information notice.
Where's the finality?
Which is the operating experience, okay? And we are always, even in Red Tag 126, you will see that operating experience should be included in the application. So that's a part of it. You know, it's operating experience. Something we have seen. And DCD in this regard is not saying.
Yeah.
It was true. Maybe later already done.
So you all are asking the other COL applicants to do this too? And SCANA and Southern?
SCANA, I don't know, but I think that Southern knows.
Any reviews that you, because this is really, this is really a construction issue, right? This is construction issue.
Yeah.
So you can, I mean, you can address how you can address it in construction, or you can address the, I mean, the operating reactor also addressing.
The operating reactor also.
Okay, the build out. Yeah, they're still addressing. If the you know, it's not it's operating experience. Yeah, it's really requirement you know. So,
Exactly.
but you know, I believe this is the data.
Okay, we don't need so much on this. Okay, so this is good because we weren't really clear about what you considered to be the scope of the concrete. What is it just like conventional or all concrete? Okay,
The problem originated from containment knowledge.
Yes, we do. You hear that?
Yes, I'm still here.
Okay, so did you hear that discussion that we wanted to, our response to apply to all concrete for Category 1 structures?
Okay, yeah, and you know, as a practical matter, you know, as we've talked, we would not plan on treating the concrete differently. We're going to apply we'll apply the testing specs to the aggregate for all concrete. But this is a matter of really what needed to be changed in the SAR itself. So I think I've got it.
Right. So now I guess it would be probably good to work with Mark offer that we're going to put this information because it sounds like it's probably be 5, 4, and in 3.8. Okay. So if you could just work with Mark, that would be great.
Yeah, I think we've already got spotted where it would go.
All right. Thank you. That was helpful. Thank you. All right. So Dan, do you have any questions before we move on to the next RNI?
No, I'm good.
Okay. So, slide 40 is sliding stability with activism.
Yes, this is section 2.5, use evaluations. The first item is the active something we already discussed in the last meeting. B is to clarify how sliding stability is evaluated. C is to provide technical basis for the value of 0.6 static position of systems. Reinforcement is needed for the quantity interfaces for additional resistance. We provided the solution analysis also they have to provide allowable demonstration to improvement and information to justify the use of static friction resistance. And the last item is to provide results of COT evaluation. To indicate we discussed the last time, the reason why we applied to look around is...
I'm sorry, we can't hear.
Okay, the reason we applied the moving average is to filter out the peaks we set in the base reaction time histories in vertical direction that resulted in lost contact between the base, in terms of calculation between the base of the control building and the subgrid. This moving average window filters out the high frequency content from the base reaction time history that produces a very short duration effects, leaving low frequency content intact, which is the one that governs the global motion of the building and thus the sliding stability. Now, during the last meeting, we were asked to see comparison of spectral density plots to illustrate how much energy was removed from the base reaction time histories by applying this moving average window. So in the next slide, we are showing comparisons. Basically, we have power spectral densities, and also we have cumulative power spectral densities. I want to point out that the blue line is the one which is unfiltered. The red lines are the ones which are with the moving average applied. Now, for the cumulative power spectral density, for the red line, we have normalized that with respect to the unfiltered time history, so we can see how much reduction actually we have in the energy. And as you can see, basically for the horizontal, we are filtering out around less than 1/4 of the energy in the high frequencies. For the vertical direction, we filter out slightly more than half of the energy. And we can go to the next slide. So we still deem that it's important to show that how this moving average window will affect the sliding stability evaluation. And we committed to do alternative stability evaluation, which will not utilize moving average window to demonstrate that what we have as a sliding stability evaluation in the EFSA are adequate. We will perform this alternative stability evaluation for the control building for the critical case, which is upper bound cell case, that uses the highest magnitude of required passive resistant pressure, which is the most critical value from this evaluation or for the design. Later on, I have the whole section dedicated to the methodology and some preliminary results from this alternative stability evaluation, which I'm going to present a little bit later, if you can wait for that. For item B, we will clarify as a response to this RI that we use two horizontal directions separate the sliding stability and the overturning stability, and that is identical methodology as the one used for the standard design, and as described in the DCD section 3.8.5.5. The sliding evaluation used static coefficient of friction of 0.6, which is the lowest among the three possible cases we have, where the foundation is in contact with the concrete field, and so that we use ASC 349 guidelines to get the value for the coefficient of friction. Then for the zone 3 and zone 3 and 4 rock, which are provided in EFSA tables 2.5.4 200 page. We don't use any shear friction reinforcement to satisfy the sliding stability of the foundation concrete to interfaces. So
I have several comments on item C. First off, ACI 349 subsection 11, that's 11.7, that's shear friction. That's the chapter shear friction. And if you look at the commentary, the values that are provided there are pseudo coefficients of friction. They're not real measured coefficients of friction. They're back calculated in order to match test results where you have dowels going through a crack and test it. So they're not real friction coefficients of plain concrete relative to plain concrete, which is, I think, the case you're trying to consider here. That's my first comment. Mm-hmm. Second comment is sort of it goes to I think you probably have that discussed somewhere else. The assumption that you're not crediting the shear keys, right, for this. And so the whole idea of having shear keys in the DCD design was to lower the critical shear point so that it is within the foundation, the subgrade material, and not at the interface between the basement and subgrade material, right?
Correct.
So now you're not crediting the shear keys, which means that you're not making sure that the shear keys are strong enough to lower that critical plane. So now your critical plane is in effect at the interface between the base mat and either the concrete fill or the underlying rock.
Correct.
Right? So it's not clear to me, like, first of all, is there going to be some sort of, like, mud mat or some sort of surface, work surface that's going to be poured in that? I mean, because I really don't know what the minimum coefficient of friction that you would have to use to evaluate that critical shear plane. Is it base mat concrete to fill concrete? And if that's the case, is it smooth? Is it roughly?
I think that the issue addressed in the DCD space, there was ROI regarding the coefficient of friction and basically the mad mass. Correct me if I'm wrong, but the whole basis of the DCD analysis was that you have these shear keys so that the critical shear plane is not at that interface. It is way down at the subgrade, in the subgrade material. That's why you use TAN of C as the basis for this. Right. Let me explain you. Basically, we have three structures. Reactor building, fuel building has shear key, and fire water service complex has a shear key. Fire service complex shear keys, we calculate forces on them, and we rely on them for the stability, and they are embedded in field concrete. Now we'll discuss that later. The control building, which is the most critical right now, does not have shear key in the standard design. The reactor building, basically, it's not that we didn't really concern about it. The reactor building, really we don't have problem with the sliding stability for that building. So it was a kind of assumption made not to take into account the shear key. Okay, so let's assume that the shear key, you're not crediting it, you're not checking whether it's okay to resist the entire base shear. So let's assume it fails. Let's assume it doesn't exist. So now your critical shear plane is the interface between the bottom of the base mat and whatever is below. Correct. Which is, I guess, concrete fill. And rock.
Okay, so you got to consider both cases.
All right.
So the coefficient of friction, what you're saying is the coefficient of friction of either of those two cases is at least 0.6.
Correct.
And I haven't seen any justification for that number other than what you're just saying, the reference to ACI 349, which in my opinion is not correct.
Okay, we will look into that. I cannot. I think there is something, but I'm not sure right now.
So I will take a look at that.
I mean, if it were just at the rock, then there is a reference to 254 where you have that. But if that's clearly, this is not going to be the case.
I think the DCD is specified 0.7 for rough and concrete, but I have to double check myself.
Okay.
Because the DCD evaluations were 0.7, they used that kind of value.
So bottom line is, if you use the friction coefficient as a basis,
Yes.
right, it should be based on likely
Yeah, and the simple, the critical point, and you can't use the data from rock, I don't think.
Yes, because it's on the...
But that's not the critical show plane anymore.
Let me interrupt briefly. For those listening on the phone and also present, we have public comments scheduled for 11:45. We're going to finish this last REI we're discussing another couple minutes, and we'll do public comments. Thanks.
For item D, we will provide the magnitude of the resisting forces described in the F section 3.8.5.5.1 and also in the DCD. We have a table for the critical moments. For the critical instances of time, we provide all these values in the review as a part of this area response. In item E, we will provide allowable lateral bearing pressures for the free concrete and zone 3 embedments. We want to mention here the stability evaluations. We get the resistance from the engineer's field above the rock. So, now, as a part of the displacement, those are results of the displacement. Just to illustrate to you that the magnitude of displacement is very small. Calculated relative to the free field motion, we are looking for displacements which are less than 1 millimeter, well less than that. And basically at the base itself is we calculate 1/10 of a millimeter, a little bit more than that. So it's a high frequency motion. It's a very stiff material. So the building goes nowhere.
Basically, the motion of the sidewall relative to the free field motion?
Right. The first two columns, and then you have what the springs are, but it depends on the stiffness of the springs. Now for the shear case, I start explaining that we basically we are using we calculate the demands on the fire water service complex shear case, and those are the two values we calculated. 43 meganewtons as a demand, and that is below was the design load used for design of this shear case, which is like approximately 50% higher.
So you're not doing that exercise for the other two structures, for the shear keys for the other two structures?
The control building doesn't have shear keys, so I've been really looking to the reactor building.
You're not relying on that for stability then?
Right.
Okay, and a sort of related question is, I'm not sure if I pointed this out the last time because we didn't really have too much time to discuss this question, but when you're, so in your stability calculations, you are relying on the sidewall pressure, at least to some extent, to provide stability, or at least the minimum factor of safety HC. So you're applying pressure on the surrounding concrete fill, specifically for the portion of fill that between the control building and the reactor building. Is that block of concrete fill going to move and push the reactor building, staying on the control building, pushes against it, and vice versa? Is that going to transfer load from the control building to the reactor building? Or is it stable so that it won't move and won't transfer it?
It will transfer some load. There are small displacements, of course, and those will be captured by triple SI analysis that we are performing. But in terms of, we will check if there is enough strain
at the bottom.
Right, so the concrete will...
One pushing against that block, and exactly pushing against the reactor. Is that what? So you are going to do that?
Yes, it's, but I think I already said to the previous one. And that is the most critical place where we can have, in terms of bearing capacity, later bearing capacity.
Okay, so that was the last slide for that RAI.
And there's one more RAI.
Let me pull the folks on the phone. Any members of the public who are on the phone, do you have any questions or comments at this point?
Yes, this is Erica Gray from Henrico.
Mute on.
I mean, obviously, I'm dealing with a lot of assumptions and numbers here, but specifically for Unit 1 and Unit 2, being that the plant's design basis was exceeded by our earthquake back in 2011, what magnitude of earthquake was its design basis for? I mean, for what magnitude of an earthquake?
It is for what unit?
For Unit 1 and 2.
We're not, those are, it's really not in the scope, Erica. Those are operating reactors that are dealt with it.
Okay, well then for Unit 3 that's being talked about, for what magnitude earthquake will it be able to handle?
I can. Erica, it's a pretty complex situation. There is no way to answer this question because what we do now in real world is that we are dealing with so-called probabilistic hazard assessment. You are asking kind of in deterministic way. This is a kind of old style of approach that we don't entertain anymore. Now, to try to answer your question in a way, I can say that in 2011, no, I believe it's 2012. Industry and NRC came up with so-called Central Eastern United States seismic source characterization, which is also published in NUREC 2115. And this covers seismic sources in the whole Central Eastern United States up to Rocky Mountains. And basically, this is the guidance which is used by all new reactors applications. Now, kind of giving you a little bit of feedback. Clearly, this area where North Anna is located is located in not in a big earthquake zone. A big earthquake zone, in a way, it's RLMEs, repeated large magnitude earthquakes. But what is considered there is so-called background seismicity. And background seismicity in this area can be at least magnitude 6 and higher. This is why everything which is designed in this area is covered basically by at least magnitude 6 and higher. If you want details, it's kind of more complicated, and actually, no matter what happened, we design everything, we require everything to be designed at least at magnitude 6, or in this case, at 6.1 and higher. Did you get enough information from my answer?
Well, I mean, not really, but I mean, I do understand that from some of the NRC's statements that I guess, for plants that are going to require updates on their seismic stuff, it's supposed to take 3 years. So obviously there's a lot of inconclusive, I guess, information, I guess, that we have at this point. So, well, not really. I understand you're talking about, the different hertz and movement and so forth. And I know that the ones we have up there already were exceeded. So, but I did want to also mention that the USGS also came out with a new paper just the other day. And it talked about strong ground motions generated by earthquake on creeping faults. And just to kind of, as a reminder, it seems like we have multiple faults that are obviously somewhat in the area. So I'm not sure how that is being addressed. And so, I mean, I guess as it goes for, as well as when we had that earthquake, it evidently caused some cracking in one of the buildings, but also something about it knocking off even some of the insulation off of the piping. So I just wanted to find out, but it sounds like we're not really going to increase. I mean, Japan never expected to get a 9.0, and so much is unknown on the East Coast when it comes to seismic, and the seismic studies aren't going to be done for years. So I guess it's just a bunch of preliminary work. But I mean, if we're not going to build them stronger than, a 6.1 or 6.2, well, I mean, that just seems like that would be erring on a real low number.
Okay, I can only add to one of your comments. Right now, you're right about USGS, but I don't know exactly what you are citing. We are working together with USGS, and I can tell you one thing for sure, that new seismic hazard maps, which will be released or already released by United States Geological Survey, are very similar in hazard to what we are doing. And there is no discrepancy between that. That's number one. Number two, just want to mention, you said 6 or 6.1. 6.1 is the lowest ground motion that we expect. This is why kind of it's the lowest level. This is why kind of in no means we designed for lowest level. That's just another comment.
So in other words, what we have sitting up there right now would not pass for the new standards that will be coming out. Is that correct?
Can you repeat again what
in other words, the two reactors that are already there, they were already exceeded by their design bases, even though everything, quote unquote, looks okay. But in reality, it looks like it's going to be more of a requirement for higher numbers as it goes for what the plants can withstand. Are you saying that Unit 3 will be designed at levels that could withstand more than, say, a 6.5 or a 7.0?
Okay, again, you are talking in different terms, but
I just want to know if these design bases are going to take into account that we've already seen somewhere between a 5.8 and a 6.1, whatever the discrepancies are there. I'm just wondering, is it going to be designed? Is the working design going to show something that's going to be a heck of a lot stronger?
Okay, yes, the answer is yes. It is designed, I can tell you that maximum ground acceleration at North Anna during the Virginia earthquake was 0.26 G. It was maximum component. And now the design is at least, I believe it's 0.57 G peak ground acceleration. This is why you can see that it is basically at least 2 times or maybe actually 3 times higher than the actual record at this specific location.
Okay.
Thanks, Vlad.
I'm sorry, who was answering my question?
Okay, my name is Vladimir Greiser. I'm a seismologist at Nuclear Regulatory Commission.
I'm sorry, I'm trying to understand you. I'm sorry, what was your name, sir?
Okay,